Hello everyone, today I'll just make a quick oversimplified basics explanation video regarding questions that go around on the internet a lot, something I might start doing now. So for the hardcore space nerds this might be a bit boring. I'll avoid the details and tangents this time, but for beginners it's one aspect of rocket science in absolute basics but fundamentally correct. I've loaded up Kerbal Space Program in the background, which I'll use as a visualization, kind of fitting since it's a oversimplified and somewhat cartoonish game, but it teaches you the very basics of rocket science in a fundamentally correct way so you can really understand them. The topic today will be the orbit of the ISS, launch windows, and why the historic SpaceX Crew Dragon launch had to be delayed and why its launch window was so narrow. So to get background visuals for this, I've just sent a little space plane into orbit, which will represent the ISS for now because it doesn't make much difference for orbital mechanics. It's just a visualizer for the background. And you'll see it's not going around the equator. Usually in Kerbal Space Program, because the game makes things a lot simpler and easier for you, you usually mostly go around the equator anyways. But in this case, I've launched it into a somewhat inclined orbit, about 45 degrees. So it's a little bit similar to the ISS, which is also in a highly inclined orbit, actually over 50 degrees. So you see, this orbit is really just one circle repeated over and over and over again, and that's also what you learn in basics of orbital mechanics. Kepler orbits, it's an ellipse. It repeats over and over and over again periodically. There are some tiny deviations in reality due to tidal forces and the like, but we'll gloss over that for now. It's not really relevant to this, and again, this is the very basics. And if we put on a little bit of time-lapse, you can see that it's really just going around the same circle again and again and again, with no real changes to that. Now, the first thing people wonder about the orbit of the ISS is why does it look a bit like a sine wave? And you can see this is just one circle, so it's basically going straight, but it's going around a round sphere and it's slightly inclined. So if you plot it on a projected map, a map of a spherical planet projected onto a square map, and you see it goes north until it gets up here, then it goes back down south, then it goes back up north, and that's why you get these sine wave-like paths when you project it onto a square map, like you see in an ISS tracker or something like that. Like you see here, you have these sine waves. They're not actually even quite sine waves, but again, I'll keep it oversimplified, so I won't get into the math behind precisely what they look like. But the next thing you'll notice is what people then ask is, why is it offset every time? You don't seem to repeat the same circle over and over. It seems to slip west and west and west with every path. And if we go back into Kerbal Space Program, what you see is the orbit is repeatedly and constantly the same, but the Earth, or in this case Kerbin, rotates underneath it, and that's what affects the ground track. It's not really to do with the orbit. The orbit doesn't change, but the Earth rotates, and so the orbit or the orbital path is gradually offset to the west relative to the ground. It really stays the same plane in space, the same orbital plane, but the Earth rotates underneath it, so on the surface the ground track seems to be offset to the west with each new orbit, because by the time it gets here again, the Earth has rotated a bit, and so it's over a different point of the Earth's surface. And as we see our launch site passing through here, that's also what affects launch windows. You see, if you launch a spacecraft to the ISS now, and remember this is our main launch site in Kerbal Space Program, we'll use that as a stand-in for Kennedy Space Center this time, you want to launch when it passes underneath the orbit. Actually, a little bit before, because the rocket needs a bit of time to even out the velocity and get to orbit, but again, we'll gloss over the details for now. So you want to launch pretty much when this launch site passes through the orbital plane, passes through underneath this repeated circular path. Now, for launch windows, this kind of alignment is actually kind of the main priority. Where the ISS actually is in its orbit around the Earth is a much lower priority. The main priority is that when you launch, your launch site must be underneath this orbital path. Now you'll notice it passes through twice a day, but you can only safely launch in one direction from Kennedy Space Center. So that leaves you one launch window per day where you can launch and be underneath this path in the same orbital plane. If the ISS ends up a little bit ahead or behind of you, that's not really a huge problem because you can catch up easily. For one part, once you launch to the ISS, you're usually in a slightly lower orbit anyways, going a little bit faster around the Earth, and you can raise your orbit into the orbit of the ISS at exactly the right time so that you've caught up, and it doesn't cost you any extra fuel, and even if it did, it wouldn't be much. So if you're a bit ahead or behind the ISS, you can correct that easily without wasting much fuel. But if you launch when your launch site doesn't pass through underneath the orbit of the ISS, let's fiddle with the time-lapse here to get a good visualization of that. Let's say I wanted to launch about now, and I just launched to the east. I'd get an orbit that passes through here at about a 45-degree angle and then goes around the Earth like this. And if I wanted to get to the ISS and not slam into it, if I wanted to synchronize my orbit with the ISS and float alongside it so I can dock to it, then at this point I would have to completely change my direction by 45 degrees, which would necessarily require me that I change my velocity by slightly less than my orbital velocity. I need a huge amount of fuel to do that. So you can correct this a tiny bit, but it costs a lot of fuel to correct these orbital plane changes. And so if you want to get to the ISS with the kind of fuel budget these rockets have, you have a launch window of at best a few minutes when your launch site is close enough to this orbital plane. It's close enough to passing through underneath this repeated circular path that you can launch and intercept the ISS without wasting a lot of fuel. Now, due to the way the launch sequence on these actual real-life rockets work, you can't really delay by just a minute. You'd have to delay either not at all or by half an hour or an hour. So in practice, it ends up being a 1-second launch window. You have to launch precisely on schedule, and if you can't do that, then you'll have to wait another day before you can launch. Not precisely a day, you'll have to wait another Earth's rotation. Again, since the Earth moves around the Sun due to the sidereal solar difference, a day and an Earth rotation is not precisely but only almost the same. But again, this is a simplified video. I won't go into those details, maybe another time, because that is also an issue people often ask about on the internet. But basically, you have to wait another day if you miss the opportunity to pass through under this orbit. If you can launch exactly now, and if you miss that by a few minutes, you have to wait another day for the launch site to just rotate around and pass underneath this point in the orbit again. Doesn't really matter where the ISS is then. Now, in this case, it's slightly different because you have humans on board, which is actually why the SpaceX launch was delayed by 3 days, not just by 1 day. Because if they had just delayed it by 1 day, the point in its orbit where the ISS is would have been a bit impractical. You could still catch up to it without wasting much fuel, but it would take a while, and that would be annoying for the human astronauts. For a cargo payload, it's not a big of an issue, but for humans, you want it to be a relatively short transfer. So you wait 3 days for the ISS actually to be in a point in its orbit at the same time when the launch site passes through underneath the orbit, so you can quickly get there. But usually, this is why, if there's no astronauts on board, usually if you go to the ISS or into any other precisely predefined polar orbit, you have 1-second launch windows, and if you miss them, you have to wait 1 day until you come around again. So in the case of the Crew Dragon launch, the launch had to be delayed for a few minutes due to bad weather, thunderclouds overhead, and a risk of lightning strike, which is pretty dangerous for a manned mission. So they had to delay it for a few minutes, which means due to the launch sequence, they would have had to delay it for half an hour at least, or an hour, which would mean they'd miss this opportunity where the launch site is just about to pass through underneath the orbit. And once you miss that, you have to wait a day to get the next opportunity to pass through underneath that orbit, and 3 days to get another opportunity to pass through underneath this orbit, where also the ISS is in a point in its orbit where you can quickly reach it. I hope this quick oversimplified explanation has at least a tiny bit cleared things up for some people who were following the SpaceX launch or generally following spaceflight but weren't really interested in the orbital mechanics before, just to get a very basic understanding of why things had to go the way they went. And as always, thanks for watching.